You know, there are these things in life that, after experiencing them, give you a completely new perspective. Like flying through the air for the first time and looking down on the world below, or seeing snow for the first time, or mountains, or an erupting volcano, whatever. This might sound stupid, but as a kid, I've had some particular experiences that made me really grasp that we are in space and in the universe. And I say it may sound stupid because everybody knows that. Even if, as a kid, you've probably heard it, or somebody told you, or you've read it, but it's not new. But there's a huge difference between being told something and actually experiencing it for yourself. Anyway, these particular things were Halley's Comet in '86, Shoemaker-Levy 9, which was broken into many pieces, which then all impacted on Jupiter in '94. In '97, Hale-Bopp, the brightest and most widely observed comet in generations, if not a century, and the total solar eclipse of '99. Admittedly, of all those, Halley's Comet was probably the least impressive. You had to watch it through binoculars, and even then it was just a point of light, so it wasn't super exciting. And I only was 7 at the time. But still, it was at the time a big thing for me, especially as all the grown-ups made it out to be a big thing. I learned that Halley's Comet was a recurring phenomenon, so it would always come back to visit Earth, but it took a long time to do so. None of the people I know at the time, not even my grandparents, were old enough to have been there when it had last visited. And as a 7-year-old, that was quite a remarkable thing, you know? It gave you a sense of scale. There are things out there that are huge and old, and even an entire human life is insignificant compared to them. Now, most people know that the Earth and the other planets revolve around the Sun, and that this is not a circular motion, but an elliptical one. And while this is not a bad starting point, in itself it's just trivia, factoids. It's there just to beg the next questions. What is an ellipse, and why do planets move on them? An ellipse is not just any vaguely oval shape, it has a very clear mathematical definition. However, in simple terms, you can think of it as a squeezed circle. In fact, I'm almost certain you've already done it yourself. Check this out. So an ellipse is different from a circle, which mostly means two things. First, it doesn't have a constant radius anymore, but the radius will vary from point to point. However, it has a smallest and a largest radius, which is called the semi-minor axis B and the semi-major axis A. Also, while an ellipse still has a center, its defining points really are the two foci, which is the plural of focus. If you pick any point on the ellipse, the sum of the distances from this point to the two foci is always the same, always 2a. An ellipse is called a conic section because you can get it from intersecting a cone at an angle with a plane. And actually, when you vary the angle at which you cut through the cone with your plane, you get different curves. Not just the ellipse, but also a circle, a hyperbola, or a parabola. And of those, there will mainly be two which will be of interest to us here in this respect, and that's of course the ellipse and also the hyperbola. A hyperbola also has two foci, but it's not the sum of differences that are the same for every point, but the difference. So if you take any point of the hyperbola and calculate the distances to the two foci, you will always get the same difference, again 2a. It has two branches, is curved around its two vertex points, and then it goes off into infinity and gets ever closer to the asymptotes, so it's becoming ever more straight the further you go out. Check this out, this will be the only equation in this entire video. This is the complete description of a system of two masses interacting through gravity. So it's a simple model of a planet orbiting the Sun, and it's called the Kepler problem in physics. Now we can find a solution to this equation, and it's not even that difficult, and it's also quite instructive, but we will not do it here. It will take a couple minutes at least, and many viewers don't care about stuff like that, so I have moved this to a different separate video. The link is where you would expect it to be. But here we'll just skip right to the solution. So, spoiler alert, you solve the Kepler problem and you get the equation for the conic sections. Depending on the energy and angular momentum of the object, it will either have a bound orbit, an ellipse, or an unbound trajectory, a hyperbola. The circle and the parabola are just limiting cases or special cases of those, so we will not discuss them separately. It would be very unsatisfying to just say, well, that's the solution of the differential equation and be done with it. So let's try to understand the solution in an intuitive way as best we can. So first, if we want to understand anything about gravity, we need to understand what gravity does. You already know what gravity does to objects at rest. They're just accelerated towards the center of mass. But what about objects that are already moving? So more specifically, objects with angular momentum. Having angular momentum means that an object is moving laterally with respect to the Sun. And in this case, we have two competing effects. So first, the momentum will carry the object directly straight forward on its current heading. And second, the gravity of the Sun will pull it directly towards the Sun. And the combined effect of those two will always be a curved line. So gravity curves the trajectory of an object towards the Sun. And all of this should be of no surprise to you because you already know an example where exactly the same thing happens. Gravity on its own. Gravity plus momentum. Any object will do two things at the same time. It will move forward in the same direction it is going. It also will fall down a bit, which will lead to this curved line. In fact, what some people enjoy pointing out is that what planets actually do is just they keep falling around the Sun. And fair point. And I'm back. I had to stop recording the video just a couple days ago and continuing it right now. So, where were we? Gravity curves an object's path towards the mass. That's the punchline of whole Newtonian gravity. With this in mind, it's quite easy to understand the hyperbolic path that some objects take. They just move in with more or less on a straight line, then interact with the gravity of the Sun, which curves the path, and then they move out again with more or less a straight line. And this always happens when the object has too much speed, too much angular momentum. For example, that's exactly the path that the asteroid Oumuamua took a couple years ago when it moved to the solar system. And for an ellipse, the only real difference is that the object does not have enough momentum to be carried away from the Sun completely. So what happens is it keeps getting curved and curved inward, and finally this leads to a closed path which will look like an ellipse. This also explains why a circle is kinda unlikely. It's basically the same principle, but everything has to add up perfectly to get the exact circular pattern. In almost all cases it will be some kind of elongated shape, some form of ellipse. And this is what all bound objects in our solar system do. All the planets, all the moons, all the asteroids, all the comets, like Halley's Comet. Generally, you can say that the planets have orbits with very little deformation, very little elongation, which is called the eccentricity of an ellipse. so it looks very similar to a circle actually. And other objects like most comets, for example, have a very high, very large eccentricity. So they move on very elongated ellipses. And that's why they're only visible for such short times, only when they are very close to the sun, and then they move out again far, far away. You may object that our problem's mathematical formulation has been way too simple because we only had one mass in the middle and one mass circling around it. But in the real solar system, we have many planets and thousands of other objects. And of course, they influence each other because gravity always attracts. Each mass attracts each other mass. Our description of the model is somewhat warranted because the Sun is by far the largest mass in our system. It has about 99% of the entire mass of the solar system is just in the Sun alone. But you also have other planets like Jupiter, which has a sizable mass, and also Mars, which is close to the Earth, which are always constantly pulling on it. The problem we have with that is we can write down the equation, but as soon as you enter a third mass into the gravitational problem, you cannot solve it anymore. There is no analytical solution for this problem. And this is called the three-body problem. And you can show mathematically that it has no closed solutions at all. And almost anything it does is chaotic. The way around it is that you can treat these secondary influences on the path of the Earth, for example, as perturbations to the simple solution you get from the two-body problem. And this leads to some small shifts in the perfectly elliptical motion of the planets, which means the ellipse does not close again on itself, but it shifts in space, it rotates, which is called the perihelion precession. A consequence of this is that the solar system is technically not a stable system. So for the next couple million years, we are somewhat certain that we do not have planets colliding or being completely ejected from the system. But in the long term, no one can really say. It is technically a chaotic system. Halley's Comet moves on its very elongated ellipse with an orbital period of around 75-76 years. It has been observed for millennia. You can see depictions of it in medieval tapestry, or it is mentioned in ancient Greek and Chinese texts, and even in Babylonian clay tablets. Famously, the author Mark Twain had been born 2 weeks after an appearance by Halley's Comet and then died the day after it returned, as he had hoped. Its next visit will be in 2061, and then it will be much brighter and much better visible from Earth because we will both be on the same side of the Sun. And I'm really looking forward to seeing it again. And this time with my little boy, because it will be the only chance he will get in his life. This means I'll have to make it past 80, which is possible, perfectly possible, but you never know, you just never know. And my little boy will be over 40 by then and might very well have a little boy of his own by then. As for the other comets of my childhood, Shoemaker Levy 9 now rests on Jupiter and will clearly not be returning ever again. Hale Bopp, the great comet of 1997, is not due again until 85. The year 4385. Not holding my breath for that one.